You need to hit the reset button. It will not stay on now. All right. Someone's in here. Hey, I see Ryan and Stacy in here already. I'm just waiting until 10:30. You might hear some family noises in the background. Don't be frightened, because I'm already frightened. No. Yeah, Janine, seeing people's faces can be okay, and sometimes, oh, it can be like this. We'll try to avoid that. How's the volume? Mm-hmm. Let's see. There we go. Good. Glad the volume's good. All right. Sorry for the quietness here. I'm just doing that typical where I stand there, wait until 10:30 to start thing. Well, while we're waiting for everyone here, I will go to camera mode. And bear with me, the camera's going to move. Yep, so there's my microphone set up. And so I have and then here is my tablet and pen system that I use. And my lovely calculator. So I have the ability to record examples on how to use the calculator, and then I have the chalkboard tablet. Yeah, if I had to do that with a mouse, that would be nuts to try to do that with a mouse. Well, in general, nuts. Yes, Janine, writing with a mouse definitely way hard. uh, yeah. All right. So I'm going to get started here. I'll clean my blackboard off here, and we'll get into this. This is actually the last chunk of material before I would have set up the exam, and the exams on the word problems that we're going to do. So what I'm going to do is we're going to go over this. Stacey has already asked some questions about ratios, and what I've asked her to do is send me some examples, and I'll work them out on videos and post them up on the links. So I'm going to try to use the PowerPoints here. I'm not a big fan of PowerPoints, and I'll be probably jumping between the PowerPoint and the Blackboard screen a bit here. And if that slows down too much, we'll adapt. But that saves my handwriting from being, well, what it looks like. So let me clear this and make it a decent color. There we go. And hopefully all the doors in the background won't drive us nuts here. Get this here. All right. So this is what we're looking at now. Chapter numbers are off. This is, I think, in your book, chapter 8. In fact, let me verify that right now by flipping into the book itself. So it's not numbered, so it lost it. Yeah, this is chapter 8 in the book. Begins on page 377 for the printed version of the book. It's chapter 11 on the online version. Now, we had worked on the properties of real numbers. We looked at them again yesterday, and we're specifically looking at the word problems that come out of them. Here, what we're really going to work on is something that we haven't focused on a lot, which were exponents. Now, everything we're doing is just one side of an equal sign right now. And that's called an expression. We had set up basic algebraic equalities, and we're going to build those with the expressions that we're building here. Sorry, I just saw a comment on changing from lime green, so I'm thinking of what other color options I have. So I guess I'd go tangerine next, right? All right, so there, I have updated my colors. And so we want to look at exponents. Now, we looked at exponents in the way that they worked on their own as multiple multiplications, the thing that I couldn't say fast. And so we have these definitions, but what happens with exponents and variables is they create something that can't be blended together, and we want to pay special attention to that. So we have had the term a variable. It's the unknown quantity or a quantity that can change in value or vary. And we tend to use X. We watched the video where X came from the translation for the unknown thing. A constant is what we've been using before, any number that's represented in one of the sets of numbers that has an exact value. And so the algebraic expressions we're doing can actually consist of things called terms. And I'm going to look at their definition of terms, then I'll show you some other terms here. And so a term is a number, a variable, or the product of a quotient of numbers of variables. And so they show a term here, show a full expression. This whole thing is an expression, and it has three terms. 2x is a term, y divided by 3 is a term, and then negative 4 is a term. A term can be any one of these components or pieces that hang out there. And let me switch over and just show you some more examples of terms. So a term that we can look at is with a power. And I'm going to write a complicated looking one here. I'm not really worried about what we do with it. And so each of these things separated by the addition signs or the subtraction sign is a term. And that's a term. This is a term. And this is a term. And so on and so on. Now, this term has two variables, x and y, and a constant of 4 that is multiplying it. Well, this term is just a constant, -4. And so terms are other parts. And let's see, we can have 3xy squared plus 9z minus 4. That's a term, that's a term, and that's a term. You can think of terms as the building blocks, and we've been working with the constants as our building blocks. We're going to look into these other building blocks that we can use, all in the idea of solving problems. We have variables now as our unknown things to help us solve problems. And so helping solve problems by putting our unknown thing in a variable, we can dig into all those rules of real numbers we have and manipulate it so that unknown thing pops out for us. That's the game plan. I mean, of course, it sounds simple, but it's a lot of small rules that combine. And so the complexity comes in all those combinations that can happen. And so here are some examples where we have the number of terms. And so here there are 2 terms because it's separated by the minus sign. And this is the constant 4 times an unknown thing called y. And here this is 1 term, and it's the variable m divided by t. And so terms get separated by additions and subtractions. Now what's really neat is how exponents and terms play together. And so we discussed exponents before. We had a base and a power. And I really want to build into what exponents can do. They're fairly useful things that we can use. When you hear things being called exponential or growth, biological, financial, physical properties tend to grow not in linear senses, but in exponential senses. You have one thing splits into 2, like a cell. Then each of those 2 cells can split into 2, and so you get this number that grows by powers, not by just multiplying by a number. And so they're very useful things that pop up in a lot of things we see coming about. And so we define the base and the power. And the power we're going to call the exponent. And so we can define it. And I do apologize, this isn't appearing good on the slide, so I'll write this back out. But for any real number, and so it has to be a real number, which real numbers, we had all the irrational numbers, all our fractions, all of those other numbers that we could use. Real numbers have anything going through. So Janine says asking, does the term exclude exponents? No, terms do include exponents. In fact, exponents will help separate different terms. X squared is completely different than x to the first power. So there's no way I can combine those 2 things into one term with an addition. And we'll look into that. So Janine's question was, do terms exclude exponents? No, exponents are part of the terms. But we want to look at the definition of exponents as we build our way for that. and we're giving names to things so we can point at them. And as you know how I am with names and definitions, I tend to look more at the process than the names. But terms are useful ways of breaking chunks in a lot of additions. So let's see, I'm still here. What I want to do is I want to write this definition a little bit better. So we look at it for any real number x and a positive integer a. So the power is only going to be an integer, 1, 2, 3, 4, -1, -2, -3, -4. It's not going to be a half. It's not going to be 2.18. Our exponents will be integers. Now there are things later on in mathematics where we can use fractional exponents, and we can use any real number in the exponent. In fact, we can even use imaginary numbers in the exponents. But we need to start with just the integers and develop the rules. And to be honest, the type of mathematics and models that have fractions up there can be simplified into terms of integers. So we won't see any of those here. I just want to say this definition isn't the final definition of a power. And so let's go here, and I will get this over. The switching's a little bit slow. Let's see, did that switch over? Yeah, it did, okay. All right. So let's move this through. Okay. Sorry about this. All right, so let me get my base here. So I have some base to a power. This is what they're trying to say in that slide. And that's equal to x times x times x times x. But the total number of multiplications are n times. Sorry about the background noise. We've got everyone home here, and I don't have an isolated office, so you'll occasionally hear doors thudding in the background. Sorry about that. And so let's compare that to the slide, because if you have the slide for the notes, I want you to see the difference here, or what was trying to be written on the slide. So on this here, it has x to some power. I used n, not a. And then you multiply x, and so on, so that you're doing that multiplication to whatever the power is. And we call the x part the base, and then we call the factor the exponent or the power. And the power is how many times we've multiplied that number. I will oil the doors, I guess. All right. Okay, so let me get here. Sorry, this switching between the two screens isn't as smooth with the layout I have. I must have moved something. It went a little bit easier yesterday when I tried this with my other class. I'll try to get between the slides and the blackboard a little more smoothly. Here, I'm going to look at A here. How A works when we're taking -3 to the 4th power. So I'm going to come over to the slide here. All right. important to note the parentheses here, because the parentheses are saying that everything in here is going to the fourth power, and we're going to have to do these multiplications 4 times. So this looks like this. Now notice, what's a negative times negative? Well, that's going to be a positive. And a negative times a negative here is going to be a positive. So if I look at the first 2 factors, they're going to give me a positive. And the last 2 factors are going to give me a positive. And a positive times a positive will be positive. And that's why we have to have the parentheses here. If we don't have the parentheses, the exponent is attached to the number, not the sign. But in this case, because I have 1, 2, 3, 4 negative signs, I'm going to have a positive answer. So this ends up equaling the positive value of 3 to the 4th, which on the calculator let's see if I can get this visible. The glare on the light's a little bit on these. Alright, let's see if I can get it focused in. Trying to get the glare over. This might not work fully. Let's see. Alright, so is my shadow helping or hurting? As we all get dizzy here. There we go, I think we can get it there. So I put parentheses. Negative 3 parentheses. Not quite clear enough. And then I put the up arrow to the 4th. And we get a, oops, I hit the wrong key. What did I do wrong? Negative 3, up arrow to the 4th. And I get 81. I will work on focusing that camera because that did not come out clearly on my preview, but my preview isn't full quality. And so negative 3 to the 4th is positive 81. So, the ability for this to come together or work its way through comes across. Why did my screen? All right, so sorry, I come back here. That's why this screen didn't come over. So negative 3 to the 4th, I'm multiplying negative 3 4 times. These give me positive values. And 3 to the 4th is 81, which our calculators are going to do. We should be using the calculators at this point. The thing to note is if I have, and I'll use negative 5 to the 3rd, that means I'll have negative 5 times negative 5 times negative 5. And a negative times a negative is a positive. But this negative times that positive will make my answer negative. And so this ends up being negative 5 to the 3rd, or negative 125. And what the rule, and we distilled this rule earlier, but I really want to focus on it here as it works its way through, is if the power is even, then our answer is going to be positive. If the power is odd, the answer will have the same sign coming across. So if I have x to the n, if n is even, the answer is always positive. Positive. If n is odd, the answer has the same sign. Same sign as the base. And what I need you all to do is to see how some of this plays out. So if I were to do -2 squared, my answer should be +4. If you type it exactly like that on the calculator, for the TI-30s, it's parenthesis -2. And this isn't the minus sign, it's the special key in the lower right-hand corner. And then you can use an up arrow. And then in your power, that should give you 4. But if you type in -2 without the parentheses, it'll give you -4. And we really have to pay attention to this, what the parentheses mean it's going across. Is my writing not coming out? Oh, you got the camera. Oh. Well, I guess I had really great facial expressions there. Thank you, Tina. The chat came off on the side. I'm really sorry, you two. To everyone. Again, well, I'll try to be more flexible. I will definitely edit this out. So let me go back here. I meant to hit this button. And I will put this back up. I had keys that were switching me between the things, and the key switching got messed up when I reloaded this. If you've noticed, when we're trying to switch screens, it's been going slow. It's new software for me. We'll get there. So yeah, they definitely better watching me, right? Especially like I didn't expect to be on camera, so I have my sweater unzipped down a bit. That's like really, everything's bad. All right, there we go. All right, so what we're going to do here is just going to walk back a little bit here and talk about what I was just writing here. So if I'm just going to go back 2 examples and redo everything, and I'm going to come back to this screen here to make this notes. The idea is if I have some base to any power, if the power is even, the answer will always be positive. If the power is odd, the answer has the same sign as the base. The parentheses play a very important role because order of operations come in here. And we can think of -2 as -1 times 2. And so if I want to square everything, I have to put it in parentheses. But we don't write that -1 out front. And so that negative sign is not attached to that number unless we trap it in the parentheses. So on your calculator, if you type parentheses, the negative sign, which is not the minus sign, it's the key. It's usually in the lower right-hand corner, versus the plus minus multiplication division, which is up the right-hand side. Usually, some calculators are slightly different, but on all the Texas Instruments, it's in the lower right. So if you do parentheses, -2 parentheses, the up arrow key, which that does vary on it. It's technically called a caret. Everything moved the wrong size now. Okay. Let's get that there. called the caret. And just type in those two differences, the parentheses -2, caret 2, and see what answer you get. And then a -2 with no parentheses, caret 2, and see what you get. Because those differences are important and we have to pay attention to them, and they relate to our order of operations. Definitely going to get my chat window on a different screen. All right, so I do apologize for you having to watch me write for about 5 minutes there. For the people that watch this lecture later, I hope they laugh hysterically. I don't think I'm going to go through and re-edit these. It takes time. Maybe someday I can buy an editor to sit down and just clip and do scene cuts for me, right? Living the high life. All right, but I want to show some examples of how the negative signs get treated, or how signs get treated. So still on the blackboard here, and for Janine's sake, I'm going to change colors slightly. I'll go into my favorite set of colors. I like the blues, always have. But you want bright things on here. All right, so we looked at -2 squared, and that gave us 4. We also looked at -5 cubed, and that gave us -125. Because there are 3 of these, I'm going to have a minus times a minus times a minus. That'll always become negative. Now, if I do -5 cubed uniquely here, that's still going to give me -125. So if these things are odd, we don't have to worry about it that much, right? We get the sign back no matter what we do. But if these things are even, well, that ends up being the same thing as 16 squared. And so when I have exponents, I kind of look at the exponent first to figure out if it's going to be positive or negative. And then I enter it as if it's going to be the positive or negative. That's because I've made so many mistakes doing this. I would really suggest, as you first learn these, use your calculator, use your parentheses, always. And eventually you'll start getting comfortable with the patterns, because patterns come from comfortability, by repeating the things we do, and coming across. That's a good promise, Stacy, but yeah, we'll see. All right. Okay, so there's that, and that. Okay, I'm going to try to switch here. I think I'll talk about the switch more so that I make it through all right. Okay. Here comes an interesting thing, how we can create exponents. And again, I'll post these PowerPoints, but I'm going to do these on the blackboard. And so what happens here is we have -2n times n. And we're going to use the order of operations and the fact that there's multiple multiplications to put powers into this. And then here we have -3 times -2 squared. I'm actually not understanding the notation on this, and I think that's the PowerPoint didn't come out. So I'm going to look at this one here, coming through as the example. Right? This is just PowerPoints being weird on different computers. I use Linux machines, so everything's always weird when you do special fonts or text on it. So let me pull over and we're going to look at this. And I'm just going to do this over here. I'll change my color. All right, so we have an expression, 2n times n. And I'm just going to say, hey, this is all going to be equal to something else. What we want to notice is these are kind of a series of multiplications. And if we look under the hood, we're saying this is -1 times 2 times n times n. We don't talk about the ones that we multiply by, just a weird convention of mathematics, right? Because anything times 1 is itself, so we don't write those, but they hide there. And I like, when we think about this negative sign in the front, to think of it as a multiplication by -1. That way I put it in the correct place. So it has a negative sign in front, so that means it's going to have a negative sign in front of it. They have nothing multiplying to get rid of it yet. Now the multiple multiplications, the factors that are repeated, right? These are repeated factors, and the repeated factors happen twice. So 2 isn't repeated, so I can plop it right there. And then the n is repeated twice, so I give it the exponent. And so it comes together to look like that. Why does it keep doing that? I literally switched the screen with writing. And when I go to the screen, yeah, I know you'll need to rewatch it, Heather. I am sorry about that. I hit this. I think I'm going to stay with the blackboard. The more of the information's there. I'll try that, and we'll go from there. Thank you for the suggestion, Tina. If there is a particular word problem, I will go to that. I'm just trying to figure out if there's a key I'm hitting, or when I put my pen down on the tablet, if it's clicking a button. That's my worry on it. So we'll just stay with the blackboard. All right. So let me just do what I was going to do originally, which is clear this out. Come back here. All right, and now I'm actually going to peek to see if it switched back. Okay, it didn't switch back. So the original problem we had was -2 and n. And we're going to convert this. Now, if I look at the little pieces here, that's a -1 times a 2 times n times n. Again, my long spiel about not writing the ones. So we have a negative out front. The 2 is not repeated. So I only have one of those. And this is repeated twice. So it becomes n squared. And so the exponents are looking for these repetitions of numbers. Now, before I realized that you weren't seeing me, one of the things that happens with exponents and variables is this answer, whatever comes out of here, isn't necessarily going to be negative or positive. The negative sign says take the opposite of what comes out of it. But there are some nice things I can see with a pattern. So notice that has an even exponent. Even exponents are always positive. So whatever I put in for n, -18, -1, 5,000, 1, it will always be a positive value. And so a negative number times a positive, this will always be negative. But if I have something like -5 times x times x times x, using the same process, I get -5x cubed. Now this will take the sign of whatever goes into it. So if this gets a -3, then this whole expression becomes -5 times -3 cubed, or -5 times -27, which is a positive 135. I'm just writing that to emphasize it. But if I switch that and put a +3 into it, negative 5 times 3 cubed, then I get negative 5 times positive 27, or negative 135. And so this exponent has, for a really, really bad dad pun, power, right? The powers has some power. If it's even, it's always going to force a positive number out. And that can tell you something about the term that it's in, what values come out of the term. But that's something that we see as we practice more and more of these, that we will get to see different things coming across. All right. Okay. This goes specifically to, we've talked about exponents. We did a few of them. I wanted to go into a little detail and specifically use them as variables. I'm going to put up a problem, and we're going to look at how to answer it and how this has to do with exponents. And these are the type of problems I'm going to have you practice in the homework for the exponent part. And so what I'm going to do here is clear the blackboard and give me a second to write. All right. This is the part I don't like about this, is not seeing anything going, so I have to keep babbling. But here we go. Wasn't I the guy in class that said I like the sound of my own voice? And here I am having to fill the dead air because I have no visual clues. So the problem we're looking at is the population of a town doubles every 5 years. And so, and you'll notice doubling rates are things that we tend to look for on how we measure things. And so you'll see that things that are exponential, we'll talk about their doubling rate. There's other ways we can talk about that, but it becomes one of the easier things. So, if the town starts with n people, how many people will it have in 20 years? All right, so there's the problem I have with my lovely penned out handwriting here. Again, this will be on the slide. So we're looking at the population of a town doubles every 5 years. If the town starts with n people, how many people will it have in 20 years? All right. So I think one of the keys here that we want to look at that help us is the word double and the time it takes to double. Now, if I double, I'm multiplying by 2. Right? If I start out with 1, I multiply by 2 to double, and I'll have 2. Then double that, I multiply that answer by 2, and so on. So what we can do is we can make a chart. So I'll say the year, and I'll go for what year it is, what my population is, and we'll look for a pattern. Okay. So at year 0, my population is n. 5 years later, I'm 2n. 10 years later, well, I've doubled this amount. Right? I've doubled between these. So I'm 2 times 2n. At 15, I'm 2 times 2 times 2n. Notice I'm doubling the thing before. That's how doubling times work. I've doubled the thing before. I've doubled the thing before. I've doubled the thing before. And so on. So I have to make sure I have all my right parentheses here. There we go. But notice these multiples of 2 that keep popping out. So writing it this way is ugly. It's confusing. And it's not focusing on the idea of the doubling. I keep multiplying by 2 over and over again. So we can think of this as powers of 2. Notice here, I haven't doubled yet. So I can say that's 2 to the power of 0 times n. And if we go back to the rules when I first introduced exponents, if I have any base to the 0 power, I get 1. Because 1 is that first factor that we had in all of our factor chains. It's the first thing that comes across in our factors. So we can rewrite all of this in powers of 2 in a way that should be able to at least mathematically help us out a little bit here. Okay. So, well, here I have 1 power of 2. Here I have 2. And so on. And so this becomes the pattern. Well, what's nice is we don't have to build this table in the future. Right? We can use the idea that if we're going to double, then we count how many times we've doubled. And what's nice is, well, we are looking at 20 years. Well, how many times would I double in 20 years? 20 years divided by 5 years means we double 4 times. Well, notice here, we've doubled 4 times. Let me see if I can. 8. Trying to add some bottom to the canvas here. See if I can do that. And let me just see if I can get that down here so I have some new space. Yeah, I can make a scrolling board. That'll work. I'll just bring it up here. And so we have this idea now that we can say, let's see, I'll use lime green for Janine, that when I have a problem like this, I can take that it's my 2 to the power of my time divided by my doubling time times what I started with. Now this looks really weird. But look what I did here. I have 2 times my time, which was 20, divided by my doubling time was 5 years. And then I had my starting number, which gives me 2 to the 4th times n. And for anything that doubles, for cell divisions, for population growth, for financial doubling, interests, we can always find the doubling time and make it a power of 2. So you'll hear a lot about doubling rates or things that are talked about. There we go, that's 100%. Let me center that. As a way of measuring how quickly the growths of processes go through. And so 2 to the 4th, that's to the 4th power here, is 2, let's see, 2 to the 1st is 2, 2 to the 2nd is 4, 2 cubed is 8, and so this will have 16 times whatever the initial population of the town was. So if the town had 1,000 people, in 20 years it will have 16,000 people. And this is how our doubling rates work their way through. So to Freya Kia. Welcome back, Stacy. That sounds like something Freya would do. I remember the myth with her and the necklace and the dwarves, so definitely sounds like a Freyan thing. So 2 to the 4th is and this is for Janine's question. And Janine says in here, I don't understand. I'm reading your chat here. Is 2 to the 4th supposed to represent years? 2 to the 4th represents the number of how many times it has doubled. So I'm gonna point out here on this in the question. Let's see if I can scroll all the way up to it here. Get used to the tools. Yep. All right. So the town doubles every 5 years. So if we're doubling, I'm multiplying by 2. But the thing we're measuring, the thing we're multiplying by, is the population. So when I look at it here, my population starts out as some number. We're calling it n. That's the nice thing about variables, is I don't have to count how many people are in the town. I just need to know how quickly it doubles. And then when I find out how many people are in the town, I can use the doubling rate to figure out how much there will be in the future. And so 5 years later, that's my first double. 2 times n. So the 2 is we're keeping track of how many times I double. Well, by the time I get to 20 years, I've doubled 4 times. So the 2 to the 4th is a multiplier times the population. But that multiplier comes from these 2 numbers, which is the doubling time and how much time I'm waiting for. And so if we come down here, when I put it together, I have 2 divided by how much time I'm waiting for, or I'm sorry, 2 to the power of how much time I'm waiting for divided by the doubling time. And that n in the front is how much the initial population is going to be. I'm going to look for a similar problem. I think one of the things about this problem is that it's meant to be generic. It doesn't look at specific numbers. It just gives a doubling time, and then projects a multiple. So let's just take the problem and give the town a population, and we'll work it out in a table, and we'll work it out in variables, so that we have both. We have a concrete example. So what I'm going to do here is I'm going to clear this. And I'm going to start at the top. All right, so let's come here. So we'll have a town. I'm going to start it with a population of 1,000, because it's a nice number. I won't have to get the calculator out for that. So the town has a population of 1,000, and we're going to say it doubles every 4 years. Right? So I'm putting some different numbers in. In 12 years, what will be the town's population? So I'm going to go right to the answer we got from the other problem. And then I'm going to back my way out to doing the table. So because it's doubling, let me change colors here. This lime green. You're right about the lime green, Janine. This doubling means that I'm going to have some multiple of 2 for the time period I'm looking for, divided by, and here, the doubling time, times whatever my starting population is. So for this particular problem, the time period I'm looking for is 12 years. And my doubling time is 4 years. And my starting population is 1,000. So this will work for anything that doubles. If I see doubling, I have to take 2 to some power. And that power is the time period I'm counting out towards divided by the doubling time. So if I plug in the numbers I have 12 divided by 4 times 1,000. 12 divided by 4 is 3. And 2 to the third is 8. Or there'll be 8,000 people in this town in 12 years. Let's do it using the table idea that the book uses. All right. So again, we're now going backwards. We're starting with the result that the book worked out for us. Yep. We're going to work our way through the table just to verify that this result works for all possible examples. So I'll have my year and I'll have my population. So when I start, I'm counting at 0 years and I have 1,000 people. Now every 4 years I double. So 4 years from there, this number doubles. And so 8 years, the previous number doubles, right? Our doubling works our way down. So if 2 times 2 times 1,000, which is 4,000. And then at 12 years, which is the time I want, I have to multiply by one more 2 in front, which is 8,000. So the little thing the book builds and the example the book uses in that example problem there is generic. It'll work for anything that has that you know it's doubling, right? Coming across. And so in this case, we gave it specific numbers instead of the generic version. And I think that might have been some of the confusion. I know it was the confusion when I first saw this problem. It was expecting something in n, and what they're doing is they're setting up basically a formula that you can use for any doubling rate. And once you set up that formula, you have the ability to continue on. And oddly enough, I'm just going to show you what the book does here. Is it just set up the idea of a formula, and that's the next section in the book is formulas. So I think that they tend to use that example as a transition. Here's how you make a formula out of nothing. You have something that's doubling. This is what doubling looks like for any circumstance. Well, if you plug numbers in, you get an answer instead of using it for a very, very specific solution. Right? We like numbers popping out of our answers, not variables. And I actually find that once I looked at how the book transitions between the two sections, I do kind of like that problem leading into what we're going to look at now, which are our formula and how formulae work and come across. So for people that haven't been watching this live, this would be a nice time for a short break. For people that are watching this live, I'm actually going to continue a little bit here. So, and we'll basically say that the time that I had the camera on was our mental break. And so let me get back to my blackboard. Let me clear this. And we'll look at the idea of formulas. Formulas are patterns in reality that people have figured out already. They've figured out a doubling rate, they've figured out other things that can be done, and they've worked their way through. And so when we use formulas, they set up ways that they can put variables in that represent other things. So I'm going to start with a generic formula. It doesn't have a real world value, but we can do something with it. So I'm going to look at 4 variables. We have x has some value, -3, I think we'll make it, -3. Y has some value, which is 2. And we'll use W and Z, and we'll give them values. And so W will be -5, and Z will be 4. And so what happens is these can represent something we measured in reality, right? They're not full variables currently, they're just x has this value. And in this case, that value is, making sure right, x is -3, y is 2, w is -5, z equals 4. And so we measured something, and they have these values. Well, formula take those values, and we have to plug them in. So let's look at a formula that uses this. So for our first one, we'll look at 2x plus 5y. Well, when we see values, this is saying wherever I see x, it's the same as -3, right? That equal sign has the word is on it. So I can say wherever I see x, it is -3. And this says wherever I see y, it's the same as 2. Notice the parentheses. I always use parentheses when I'm putting something into a form. Well, I should say always. You get sloppy once you do these things over and over and over and over and over and over again. But in general, I try to put parentheses in because it helps me with negative signs. The things I'm measuring has a negative sign in it. I want the parenthesis around the negative sign. But at this point, I've taken the formula, the 2x plus 5y, and I have, or the expression, and I have now replaced it all with numbers. And we call this process evaluation. If we have some expression or some formula and we can plug numbers into the variables, we evaluate it. So 2 times -3 is -6. 2 times 5 is 10. -6 plus 10 is +4. And so we're able to evaluate that. Look at another one here. Which is 2w squared minus 3y cubed. So this is an expression. Depending on what the values of these variables are, it can hold different values. But I've gone out and I've measured these. So wherever I see w, I replace it with -5. But notice the power. And wherever I see y, I replace it with y. Again, noticing the power. Well, what's nice here is a negative squared will be positive. So this is 2 times 5 squared. And so I've taken care of my signs. Remember how I said I like using the rules to take care of my signs? What's really nice is you can enter this on your calculator now, right? On your calculator, you can go 2 times parenthesis -5 up arrow squared minus 3 parenthesis 2. Whoops. I've got one small thing here. I need my times. Parenthesis 2 up arrow 3. And that would give you the same answer. And so this is 2 times 25 minus 3 times 8, or 50 minus 24, or 26. And so this process is called evaluating algebraic expressions or using formula. Now, sometimes these formulas can come from something in reality. So I'm going to show another example problem from the book and see how it comes together. Let me see, did I give myself enough space to scroll? No, I didn't. Okay, I will clear this off. Okay, it's not clearing. This is when you kick the computer lightly. There we go. No, Janine, I did not kick the computer. That was for comic effect. And I'm actually seeing if this expression is in the book versus being on the PowerPoint I was using, because I don't want to flip back and forth on the screen there. I do think this is example 4 in the book, example 5. Flippy, flippy, flippy. Oh, well, I have it on the PowerPoint. Or, yeah. Ah, there it is. It is here. Good. Okay, so I don't have to flip back and forth. All right, I'll make the PowerPoint go away on my side. All right. So, physics tells us if we shoot an object straight up. Now this is example 4 in the book. So if you hate my handwriting, between the slides in the book we have it there. Straight upward at 100 feet per second. Then its height will be found. I want to turn this into a formula. The book does it as an expression, so the book doesn't do this side at all. It just says its location, but I'm going to preview formulae for us. And I'm actually going to talk about what formulae do. And so here I have a variable that tells me my height above the ground, and t is my time in seconds. And so the question is, how high will our object be in 5 seconds? Oh, so seconds is time, so I can say, hey, t equals 5, and so my height is going to be -16 times 5 squared plus 100 times 5. So I'm taking this value I have for t, and I'm substituting it. So h will be negative 16 times 25 plus 500. And I cannot do this without a calculator. Even though I have the answer in the book. So I get negative 400 plus 500, or 100 feet. And so the object will be 100 feet above the ground. And this is what evaluation lets us do. It lets us measure things coming across. So 16 is a given. So Janine asks, how did I get 16 in this? And so what we want to look at here is it's a given. This is actually so what I'm going to do here, Janine, is I'm going to pop the problem up on the screen here. And so physicists have shown if an object is shot straight upward at a speed of 100 feet per second, its location after t seconds will be this expression. How far above the point of release will the object be after 5 seconds? So the 16 is given as part of the problem. And I could answer your question in a little more detail here. Is that this actual thing here has a more general form, which is negative 1/2 a t squared plus whatever velocity we start with plus t. A is always the same everywhere on Earth. It's 32 feet per second squared. So when I take half of 32 feet per second squared, I will always get 16. And so the problem doesn't go into all that background. For what we're doing, we don't need to know it, but that's where it came from. And so the problem gives us this. Let me put that in a big, for Janine, lime green, since you mentioned that color. The book gives us that. All the numbers are given out of that. Yeah, it does make sense a bit. I mean, these things have to come from somewhere in reality, and then we use that coming through. Evaluation is really looking at trying to find things that are already known and finding what you can measure with them. So what I'm going to do here is I'm going to put one up on the screen on the slide, and copy it on your notes as you want. And then I'm going to go over into the Blackboard to do it. What I'm going to do is I'm going to use the interest one, because the interest one comes up a little bit. So let me see if I can get that up on the screen here. Again, these examples are in the textbook. So yeah, all right. So I have that there. On the online textbook, all these examples are in here verbatim for here. I use different examples, or I'll use problems from the worksheets when I'm up on the Blackboard, because I have access to these slides and I want to show them to you. I'm going to use these examples. But if you need other examples, especially from the problem sets, just text them to me. I'll try to make a couple videos for them. The key to these, if we look at this, is it gives us a formula. And that formula right here is the interest equals the principal times the rate times the time. Where that comes from, we could talk about it. This is very similar to when we did percentages, and we have the rate times the base. We have a rate times the base here, the p times the r. We just have to do it for a variable amount of time. So we have the interest equals the principal times the rate times the time. And this is very similar to a percentage problem. We just have this extra two pieces here, the RT. But what's nice is once we have a formula, once we have a relationship, we just need to measure the things we need to get out of it. So if we look at this problem, it gives us our formula, and it says, hey, find the amount of interest, which is going to be I, on a principal of $3,000, which is going to be P, that's been deposited for 2 years, well, that's T, at a 6% rate. So we have a formula, and we measure things that can go into the formula. So let me clear my blackboard here. You're not seeing the clearing of the blackboard yet, but I will be over to it in a second. There's a nice clear backboard. Okay. So I'm going to be looking at this problem where we have the interest rate, we have everything set up. So in this, I have I equals PRT. That's the formula I'm giving. And I do not know I. But my P was, let me make sure, $3,000. My rate was 6%. And my time was 2 years. All right, notice a percent. We're going to need to change that to its decimal representation. Whenever working with percentages, turn them to their decimal representation. So I can plop this into there. So I get 3,000. I can take my decimal representation, 0.06, and so let me make sure, pointing to where everything goes. They fill in for the variables. And if I do my multiplication correctly, I get, even though I have the answer in the book, I'm still going to use my calculator to double check, because double checking saves lots of headaches. So I get 360, and that's in dollars. So the interest would be $360 on $3,000 at a 6% rate for 2 years. So our job in formulae, our job in expressions is to find the formula. Usually in what we're going to do, your formula is going to be given. I'm not asking you to memorize formula. What I'm asking is to use them. Then in reality, you measure those things and you plug them into the formula. And that's how the word problems will work with these. You'll have a formula, and then you get the measured values and you see what the output is. All right, that's everything I have today. What I'm going to do is on Monday, we're going to do the last section in chapter 11, and then we'll do a little bit of review. Do you have any questions in here coming across? Stacy, please send me some of the problems you have with ratios, and I'll try to record something this evening and link it up on the YouTube stuff. And I guess if I wanted to be polite, I could do it like this. Okay. So if I'm talking to you, you see my face. I really don't like this. Like I need like television makeup toupee or something. If you don't have any questions, you can plop out. I'll end the stream. Thank you, Stacy. Thank you. Like I said, I probably won't get to it until the evening. But if you're good with everything, drop out. And once the numbers go down, I'll end the stream and it'll be posted up there. I will definitely just use the blackboard in the future. I think it's much smoother just using the blackboard. Me staring at the chat. Yes, I'm actually gonna make everything due end of the week. You know my due dates are gonna be flexible. I think the only thing that's gonna be inflexible will be the exam. The exam will be due at the end of a week. My end of the week is Sunday night at midnight. Oh, you're very welcome, Tina. I'm trying my best to make this stuff work. I definitely do not like my face on these things. Can we just do this? Cool, cool, Janine. Again, double check, make sure all the homework is out there. I thought I put up a quiz that was going to be like the in-class worksheet of one of those for the stuff we did today. And the test will be clearly labeled a test. I will probably have that up in the next 45 minutes, but still want to walk over like one more thing before we do that. Have a great time, everyone.